Hi, I'm Emma Young, and I want to create a photokaridescope for less than $25. To do this, I based it on a simple Placido disc, which is used by many clinicians to analyze the shape of a cornea by using reflective rings, and a clinician can view the cornea through the small holes. For a normal patient, the rings are round and concentric. If the rings are distorted, the patient might have an irregular astigmatism. One of the many advantages to using a Placido disc is that it analyzes a large area of the cornea, opposed to a keratometer, and some of the disadvantages are that it's not quantitative and there are no printed results, so you can't really analyze it later on. There are other models of Placido discs other than this simple one. Just a plain Placido disc is a flat disc that can sometimes have an ad lens on it. There's also a Klein karidescope, which is a battery-powered Placido disc that is also backlit and can be observed with an ad lens. And there's also the Van Leeuwen karidescope, which is illuminated by a slit lamp. Polaroid photokaridescopes can also be used. Some of the advantages are that it provides a permanent record of the Placido disc reflection in a form of a Polaroid photo. There are a few disadvantages to this, such as that it's really large and also that it's really expensive and can be a problem for people in third world countries to get. My first step in trying to create a photokaridescope for under $25 was to determine the needed vertex distance. The cornea should fill up most of the image, and in an unfocused iPhone 7 photo, the distance was determined to be 2 centimeters. We needed to determine the power of an external ad lens. To do this, we had to determine the distance between the Placido reflection and the cornea, and add this to our 2 centimeter vertex distance, which was measured in the previous slide. We also need to calculate the cornea as a minus mirror, as well as the divergence of the Placido image striking the cornea, and finally measure the power of the iPhone's autofocus. To do all of this, to determine the external the ad lens, we followed the following formula. We did the external ad lens equals 1 over the vertex plus the image distance in meters minus the iPhone autofocus. As you can see here, we did the calculation of the cornea as a mirror. We followed the equation D equals 1 over R, and we assumed that our R in just a normal cornea would be 8 millimeters. And by following this equation, we determined that the cornea has a power of negative 250 diopters. We then determined the dioptric equivalent of a 2 centimeter vertex distance. As shown here, we used the equation U plus D equals V and plugged that in, so we determined that our diopter value would be 1 over 0.02 meters, and it ended up giving us a value of 50 diopters. We then needed to calculate the divergence of the Placido disc as it was striking the cornea. We did this by using some of our previous calculations, such as the negative 50 diopters and the negative 250 diopters for the cornea, which was calculated in the previous slide. Using these, we were able to determine that the total reflection divergence must be negative 300 diopters. We then needed to calculate the size of the Placido disc by creating a 7 millimeter image. I'm going to let you guys pause this slide if you want to analyze it more and understand what math we did. We then calculated the divergence between the image and the camera, which was equal to 1 over 50 meters plus 1 over 300 meters, which ended up equaling 0.023 meters or 43.5 diopters. We finally determined how close an iPhone must be to autofocus an image, which was 7 centimeters. The image taken shown here of my notes to determine this was actually taken at 7 centimeters. As I'm sure you know, 7 centimeters also equals 0.07 meters, which equals 14 diopters. Let's fill in some of the values from the formulas we were trying to solve for earlier. Our calculation of our cornea as a minus mirror was negative 250 diopters. The diopter equivalent of 2 centimeter vertex distance was negative 50 diopters. The calculation of the vergence of Placido image striking the cornea was 43.5 diopters, and the measurement of the power of the iPhone's autofocus was 14 diopters. If we plug all of our values into the equation shown here, we end up getting 43.5 diopters minus 14 diopters, gives us an add lens of 29.5 diopters. We then needed to determine the distance that the rings must be for our photokaridescope. I'm going to let you guys pause the slide once again so you could go through this and understand it more thoroughly. Once we had completed all our math, our project looked wonderful on paper, but of course it needed to come together, being that it was an engineering project. So first we ordered our lens that was the calculated power, and it didn't fit. We used a ring light that's actually used for selfies, and it was hard to attach the lens onto this ring light. We tried to use a Google Glass lens, which had a very similar power to the lens that we had calculated, but it also didn't fit on the ring light. We later found a ring light that had a built-in lens, which had a power of 40 diopters rather than our 29.5, which we'd originally wanted, but our ring light that we found worked just as well. After finishing almost all of the project, all that was left was the ring distance, which may sound fairly simple. Originally, we tried to use evenly spaced black rings. These rings did not end up being evenly spaced on our cornea. It was hard to see these rings, and the rings were way too far apart. It seemed as though there were too many rings, and only a few of them were actually on the cornea. We decided to switch to white rings instead of black rings because it was much easier to see the white gap between the rings instead of the actual rings on the cornea. While these rings were much easier to see, they still weren't evenly spaced, and there weren't enough rings now. What we then tried to do was we calculated the ring distance, which was shown in the previous slide, and we added more rings to it. With this, you were able to see the white rings on the cornea, the rings were evenly spaced, and there were more rings. Thank you guys so much for listening to my presentation.